Since practicing the free body diagrams is very important in terms of being able to set up problems, I want to do a few more examples, and I just didn't want the last video to be even longer than it was. So let's start with this question. Again, please pause the video, come up with your own answers, see if you can figure it out before listening to the solution. But I will definitely walk through this with you. All right, our object of interest is the ball. So my dot representing the ball, I can totally draw it right here if I want, that's fine. Draw it over here. I tend to draw my free body diagram off to the side often. The forces. We need to recognize the forces acting on the ball. Those forces fall into the categories of field forces, meaning the force of gravity, specifically in this case. The other field forces are electricity and magnetism, which that's not something we're working with here. Other forces are all going to be contact. So we are drawing the free body diagram for the moment shown in this picture they've given. The other object, the only contact, I guess I should say, that this ball has with anything is the rope, the string. So we need to ask ourselves what the string is doing to this ball at that moment. So strings, ropes can only pull. So the force that the string exerts has to be away from the ball, along the string itself. We call this tension. So there's nothing else in contact. I mean, the only other potential force would be air resistance, but again, we're going to still ignore air resistance. So this is what my free body diagram looks like. Coming back to my options, B is the correct answer. Now, just as a side note, if you chose C, D, or E, it is common to want to put a vector in our free body diagram that would represent where the ball's headed. Of course, if I pull the ball to the side and release it, it's going to start swinging down and then up on the side. But we do not include vectors that represent the velocity or acceleration or which way it's going to head. We only include the actual forces. So our contact force with the string and our field force with gravity. Let's look at another example. Read through this. I recommend thinking through how you would label all those vectors as part of choosing your answer. But pause the video, choose what you think the answer is first, and then watch the solution. All right, force diagram or free body diagram for the block. That means my little dot represents the block. The block is the object of interest here. I'm going to start with gravity. That's our field force. We can't turn off gravity. Everything else is going to come because of contact. So, for example, we have a string again. This string is attached to the block. Strings can only pull. And so I need to draw my string force directly along the string, which is directly left. That we would label as tension. The block is also in contact with the surface. So the surface, we always have a normal force Again, the name normal force comes because the direction of that force is always perpendicular to the surface. So I would draw that this way. The other potential force that can be created with the surface would be friction. But coming back to the problem, it says this block is held in place on a frictionless incline. That might be really weird to try to imagine, because that would have to be some sort of really, 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 really perfectly smooth surface. So not particularly realistic. But because they're telling us it's frictionless, we will not account for any friction force. This block is not in contact with anything else, so the three forces acting on it we have represented. So coming back to our options, that leads us to E being our answer. So one other side note really quick. Because the problem says the block is being held in place, meaning it's not moving, it's not going to move, it's just sitting there, we know that the net force would have to be 0. In terms of components, we could say the normal force has a y component and an x component. If the block is not going to go anywhere, it has no acceleration, that would lead us to say that the normal force to the right has to balance out the tension force to the left. Those are the only forces in the x direction. If there's not an acceleration in the x direction, then the forces must balance out in the x direction. Similarly, there's no acceleration in the y direction, means these forces need to balance out in the y direction. So reasoning through balancing forces can help us come and jump to relationships really quickly. Now, of course, in this problem, we're asking just conceptually about the free body diagram, but the reasoning through further between forces and acceleration is going to come into play into answering questions. All right, let's go through one more example of free body diagram specifically, where we're recognizing forces. Here is our question. All right, so we have our car parked in the hill. This problem doesn't explicitly state that we want the free body diagram of the car, but hopefully it's obvious that that's what we're talking about, since there's no actual individual little objects to talk about. So I'm going to draw my dot representing my car. I'm going to go ahead and jump to mg, the force of gravity. The field force, the earth gravitationally attracting the car. All the other forces are going to be related to contact. This car is in contact with the ground, so we know there has to be a normal force simply because there's a surface that the car is resting on. And just a reminder, the name normal force comes because it specifically makes a 90-degree angle with the surface. So the normal force here is up at an angle. Now, the other thing that's important here is that it tells us this car is parked, meaning it's not going anywhere. It's just sitting on the hill, it's staying on the hill. So there has to be some sort of force that does not allow it to go down the incline, down the hill. We remember, hopefully, from chapter 2, when we talked about acceleration on the slope, we know that an object on a slope or incline is going to accelerate down the incline if it's frictionless, which of course that means we wouldn't be able to park the car. So there must be a force that's not allowing the car to accelerate down the incline. That force needs to come from the ground as well. And so that will specifically be friction. This force, this is specifically static friction. If the car is not sliding, that static friction needs to point up the incline specifically in order to counteract what the force of gravity, that pull down the incline. There's nothing else in contact with the car. So this is our free body diagram. Let's see, that's option C. In terms of balancing forces, we know since the problem says it's parked on the hill. So this is a side note, this isn't part of answering this specific question. But if the car is parked on the hill, its acceleration is 0. That means the net force on the car has to be 0. We mean that the forces need to balance each other out. Now we can totally break the normal force into X components and Y component, and then friction into an X component and a Y component. We would say then, in order to balance out our forces, that the upward Y component of the normal force and the upward Y component of the normal force, those two together acting upwards on the car would need to balance out the force of gravity pointing downwards on the car. So this would represent balancing the vertical forces or Y component forces. We would need to balance the X components as well. Again, because in this specific problem, the car's parked, that leads us to knowing the acceleration is 0, which means the net force has to be 0. So looking in my free body diagram, we have 2 X components of forces. So we would say that the X component of the normal force would have to equal the X component of the friction force. This balances the horizontal forces. Now, in a previous video, you might remember, or even in the previous, I can't remember when I said it. I think it was the previous video. I mentioned that we will commonly rotate our coordinate system when we have an object on an incline. I just want to walk through that here because it will help you see why to rotate. So I'm going to put my x-axis along the incline, down the incline being positive x. That makes the y-axis perpendicular to the incline or hill. That means the angle of the incline, whatever this angle makes with the horizontal, so the car, whatever angle the hill makes with the horizontal, will be down between the new y-axis and where mg is. So we will have a y component of gravity right here. That would be mg cosine theta because it's adjacent to the angle. The x component has to be parallel to this x-axis. This x and y component has to meet at a right angle. So this side will be mg sine theta because it's opposite the angle. In this coordinate system, the forces have to be balanced as well. So if we balance the forces, I'll just say balance y forces, because it's not vertical. Over here, I used just x being horizontal and y being vertical. Over with this new coordinate system, y is not vertical. So I'm just going to say balancing the y forces because I know this car is parked. It has no acceleration. The forces still have to be balanced regardless of what coordinate system I choose to use. So in the y direction, I have this normal force pointing in the positive y direction. The only other thing pointing in the y direction is that mg cosine theta pointing in the negative y direction. So I would say the normal force is equal to mg cosine theta. Those have to balance each other out, because if they didn't, there would be an acceleration in the y direction, which would mean the car would be taking off that way or this way, which of course is not happening. Similarly, we want to balance the x forces. In the x direction, we're talking this rotated x direction, we have this component of gravity down here, the mg sine theta, pointing in that positive x direction. That has to balance out with the static friction force pointing in the negative x direction. Notice, when we look at these, we have this, just the normal force related directly to mg cosine theta. We have this friction force related directly to mg sine theta. If we come back to the situation where we kept a traditional x and y axis, we end up with the normal force having x and y components, the friction having x and y components, and mg not. So setting it up with the traditional coordinate system, we increase the number of x and y components, typically. By rotating our coordinate system, our x and y components typically we minimize. We certainly still have x and y components, but we minimize how many vectors we need to break into x and y components. So ultimately, it just simplifies the algebra a bit when it comes to calculating and analyzing forces in motion on an incline. So general rule of thumb, object on an incline, a slope, a hill, rotate the axes. We will be doing more examples to show this, but again, I just want to get that into our head to remember, and hopefully, as we continue seeing problems on an incline, we'll remember to do that. All right. Please feel free to ask me questions. Please ask questions. I'm happy to meet with my students on Zoom. Just send me a message and we can arrange that at a time that would work for both of us. I'm happy to do that.